Hello everyone, we are here to present our paper, A Distributed Framework to Orchestrate Video Analytics Across Edge and Cloud, a use case of Smart Doorbell. The concept of Internet of Things is a reality now. This paradigm shift has caught everyone's attention in a large class of applications. Due to such a huge growth in this segment, many video based doorbell solutions are commercially available in the market. The existing doorbells face many problems. First of all, the contemporary offerings are quite expensive, thus limiting the widespread use of smart doorbells. Second, the existing technologies are bespoke, thus offering limited composability and reusability of a smart doorbell framework. Also, they are monolithic and proprietary, which means that the implementation details remain hidden from the users. Thus, to address this challenge, we propose an approach that provides multi-layer design and implementation. A multi-layer design is implemented to manage and deploy video analytics applications across edge and cloud. The proposal is based on state-of-the-art technology and uses AWS as a base platform for the implementation. Let us now look into the state of the art architectures used for video analytics on IoT devices. First, on device machine learning techniques. Here, a machine learning model is trained and executed on the edge device. The efforts belonging to this category often focuses on designing a simple model that can run on IoT devices. Some of the technologies for on device machine learning techniques are Har Cascade, Hawk plus SVM, and SIFT. Second, on-device deep learning technique. This approach employs various model reduction and compression techniques to enable its deployment on IoT devices. In this approach, also, the deep learning models are trained and executed on the edge device. Some of the technologies for on-device deep learning techniques are MobileNet SSD, YOLO, etc. Third, on-device edge computation. To address the challenge of deploying a powerful and large deep learning model on IoT devices, this approach considers offloading deep learning models from an IoT device to more powerful entities or edge device. In our scenario, an IoT device sends a video stream to a nearby edge device. The edge device processes the data and sends back the corresponding results back to the IoT device. Some of the tools for on edge computations are Google Coral, NVIDIA Jetson, etc. And lastly, cloud based software as a service. This approach leverages cloud based software as a service for video analytics. Various cloud vendors such as Amazon, Google, Microsoft have developed deep learning based platforms. A typical approach is a device sends a video stream over the network to a cloud based platform where all the processing takes and detection results are sent back to the IoT device. Some of the technologies for cloud based software as a service are AWS recognition, global vision AI, etc. Now, let's move forward on the design and implementation of the doorbell. The proposed system consists of three layers, namely device layer, edge layer, and cloud layer. Let us dive into the implementation of each layer. First, the device layer consists of a camera module to capture a video and has a PIR sensor to detect the motion of an object. The camera module is triggered by the motion sensor when a motion is detected in the proximity of the doorbell, thus avoiding the processing of redundant and uninteresting data. The edge layer then processes the transmitted media data before the data is sent to the cloud. The functions of the edge layer are frame sampling of a live video stream from the attached camera and sending raw footage to the object detection component. The current version implements four object detection models that are face detection and recognition, animal detection, unsafe content detection, and a noteworthy vehicle detection. The object detection components implements functions that leverages AWS recognition APIs for object recognition and detection. And lastly, the cloud layer or serverless architecture. The proposed approach leverages AWS Lambda, which holds the application logic and is triggered in response to the corresponding event. The cloud layer is also responsible for providing scalable storage to access data anywhere and anytime, reliable processing infrastructure to train new machine learning models, and API interfaces for user applications. The AWS cloud based software as a service provides persistent data storage and access services like Amazon DynamoDB and Amazon S3. It receives video analytics metadata from edge and provides a scalable storage to access data anywhere and anytime. The smart doorbell comes with a mobile application that receives an alert notification when a motion is detected in the proximity of the doorbell. This alert notification functionality is implemented using AWS Kinesis, AWS Lambda, and Amazon SNS. The AWS Kinesis data streams is used to ingest video analytics metadata from the edge layer to the cloud layer. The AWS Lambda function then processes the metadata in response to the data ingestion from Kinesis and triggers push notification. Finally, the push notification service is executed using AWS Simple Notification Service. In our approach, we have also implemented a voice assistant functionality, which allows the user to interact about the smart environment that they are in. We have implemented this conversation interface using Alexa voice service. The smart doorbell comes with a mobile interface with an admin panel that allows the user to add faces with friends, family, and visitor categories. The added faces are then updated to train the face recognition module. The mobile dashboard provides the details of the activities at the doorbell. It also offers on demand live video streaming functionality. The alert notification functionality allows visitors to announce their presence and request entry into the building, as well as enables the occupant to verify the identity of the guests and to help prevent home robbery or invasion at a moment's notice. Now, let us move towards the evaluation results of the proposed approach. First, let's talk about the model accuracy. The above table summarizes the performance results of AWS recognition model for our scenarios. The model outperforms in terms of precision because the model does not incorrectly detect the presence of an object in an input image. AWS recognition has accuracy above 90% in all scenarios. AWS recognition has a recall value above 80% in all scenarios. This graph provides the comparative analysis of the AWS recognition based proposed approach with respect to the state of the art approaches. Here, overall model performance is an aggregate measure that considers both recall and precision metrics of a model. The graph compares different approaches with the proposed AWS recognition based model, including well known models such as MobileNet SSD, HAR Cascade, and Hog plus SVN. The evaluation result shows that AWS recognition has the highest F1 score among the compared approaches, indicating that the models perform well both on precision and recall. And latency is the length of the time it takes for a data to be sent to the server plus the length of the time it takes from the server for the data to be received. The result matches our intuition very well, showing that AWS recognition model exhibits high latency with respect to on-device machine learning and on-device deep learning approaches. The primary reason of having high latency is because the communication between AWS cloud and the doorbell over a network. Here, this table compares the memory and CPU usage of different approaches with the proposed AWS recognition based our algorithm. The result matches our intuition very well that deep learning based algorithms require more memory and CPU because of its CNN based deep neural networks, which may not be a good choice for highly resource constrained IoT devices. On the other hand, AWS recognition based algorithms consume very less memory because it offloads the video processing task on cloud, which makes it suitable for resource constrained IoT devices. Thus, to conclude, we have proposed a distributed framework to orchestrate video analytics across edge and cloud resources. The evaluation results demonstrate our intuition very well, showcasing that AWS based our approach exhibits high latency, low memory, and low CPU usage with respect to the state of the art approaches. These results show that AWS based approach is quite suitable for applications such as smart doorbell. Here, apart from all the advantages, the limitations of the cloud based software as a service are high latency and high subscription cost of using cloud platform services. Secondly, Privacy is also a major concern in the video based smart doorbell application, as there is an involvement of the biometric data of homeowners. Therefore, in the future, we plan to design a distributed edge based framework for low cost, resource constrained IoT devices for video analytics application.
Thank you.